Well, good morning. Thank you all for coming out to the first session of the morning. I feel like I need to start with the fire and brimstone here of Intel SGX. I'm particularly impressed that you would show up for a talk that had John Updike in the title. I actually threw that in a little bit sort of like for my mom. My mom was an English major and an editor for Simon & Schuster, and she used to school me on John Updike and others. But it's actually pretty appropriate because the Poetically Opaque, because what I'm going to talk about this morning is a new security feature that was released by Intel in November called SGX, Software Guard Extensions. And in my opinion, it is a rather elegant and sort of a poetic way of helping lock down security for your applications and data. It actually will stand up what's called opaque black boxes in the application stack. And it's, I think it's pretty powerful. It's brand new, so it's sort of like a green field for development or for some projects that you may want to start doing some research on, because I think it really is going to be a fairly a good game changer for securing systems. So with that, a little bit about who I am. Officer, eventually manager, then got into software security research for the agency. Along that path, spent a lot of time with NSA on some research projects, got involved with some of their operations, and also with SOCOM, supporting our soft war fighters. I then moved on to Blackbird Technologies. They're sort of a boutique company there in Northern Virginia, again, supporting some of my old employers, doing some very interesting things. They were acquired about 1.5 years ago by Raytheon, which is another really good company doing some great work. I'm currently working at VMware as a solutions architect, supporting the intelligence community and DoD soft community in particular. I should probably note that my talk really has nothing to do with CIA or CIA work, or my work with NSA or DoD. It's sort of like a disclaimer, and certainly not with VMware. I'm not going to be talking about any VMware products this morning. Although I will say, since arriving at VMware, I started talking to some of their PSXi engineers in Palo Alto about questioning about, are you going to provide support for SGX in your hypervisor? VMware has always been a little reluctant to talk publicly about coming future features, but they did say, and it was okay for me to say, that they are looking at it. It's very difficult for them, but they are looking at it very strongly. And I'll talk a little bit about some projects that some other companies are doing, and I think VMware understands they sort of need to get on board with as well. So why this talk? Obviously, what we're doing today in terms of securing our systems and our data is not working. It's definitely not working. You see all these spectacular breaches, and they seem to be increasing in magnitude and impact. Now, certainly by layering on Intel SGX and those sort of things, it's a lot like doing sort of more of the same, but it's a little bit, I think, a little bit better in how it operates. It's very discreet in what it's trying to protect. And as you'll see, it's fairly actually pretty easy to implement. And not to sort of reignite an old flame war about hard G versus soft G in the community. I was just curious about that lower publication, whether or not that should be a hard G or a soft G. But I'll leave that up to you. As I said, SGX is a fairly new technology. Although Intel's been working on it since probably around 2012, they just released it in commodity processors in November of last year. And there are some platforms available today that do support it. And in fact, the laptop I'm demonstrating on here, my presentation laptop, is SGX compliant. So although there's a lot of processors out there, and I'll show you a little bit later, that does support SGX, not all the motherboards or BIOSes yet support it. So you have to be a little bit careful there. But again, I have a list for you of the machines that are available, commodity machines that are available that do support SGX fully. And it's not expensive. In my opinion, I think SGX it's probably the most impactful technology release from Intel involving security and functionality since VTX. And as you'll see, the way that they've implemented SGX and how they've rolled it out is very similar to what they did with VTX. So what I want to do is sort of level set first why it's important that we take advantage of SGX and both impacts, both in the intelligence and defense communities and in the private sector as well. Of course, it's nothing new. The pundits and the analysts have been talking about this new cyber Cold War for a number of years now. And while it's true in the larger geopolitical sense that there's this new cyber Cold War, what I want to focus on in this talk is sort of the game within the game, the little CI or Cold War struggle that's going on at the working level, both at the agency, NSA, and in private sector, in protecting our tools, our capabilities, and our intellectual property, that small subset of the Cold War. And make no mistake, everybody here is involved in one way or the other in this new cyber Cold War and how it's playing out. The legacy cyber Cold, or the legacy Cold War was fought primarily between proxy adversaries in places like Africa, the Middle East, Latin America, certainly in the front lines between NATO and Warsaw Pact. This new cyber Cold War, however, is being fought really, literally between the two sets of adversaries, between the U.S. government and the U.S. industry and Russia and China. And so the stakes are really high in terms of flap potential when these things happen, if we can attribute them properly. And the potential loss of tools, data, intellectual property, and value for companies is huge. It's absolutely monstrous. So again, in the private sector, well, in the intelligence community, they're worried about the tools and the capabilities that they've developed to work against their adversaries, trying to protect those capabilities from compromise, from reverse engineering, and the impact that entails. In the private sector, of course, the threat is to intellectual property and the secret sauce. It's sort of like for the Coke, the secret formula for Coke is up for grabs. McDonald's special sauce for their hamburgers, or Pied Piper's Inside Out algorithm. So it's inside out? Thank you, yes. So those are the kind of things that industry's trying to protect. But when industry loses their intellectual property, that has an effect on the U.S. economy and the U.S. National security. So, as I said, in one way or another, all of us involved in the cybersecurity, whether it's developing offensive capabilities or developing defensive capabilities, whether you're red or blue, you're involved in the cyber Cold War. And make no mistake about that. I was at a recent NSA DoD cybersecurity conference. Actually, it was about 2 weeks ago. And one of the speakers there made the comment that it's estimated that each year $1 trillion in intellectual property is stolen through cyber attacks. $1 trillion. So of course, you know, there's this tension between the need to get our tools, our capabilities, our products, our software out into the market space if you're in the public sector, but if you're in the private sector, if you're in the public sector, and intelligence community, DoD, you have your offensive tools that you've put out there, and as soon as you do that, obviously you're leaving them open to capture, compromise, reverse engineering, and it's a big problem. It's almost like signals intelligence, right? You can't send out a signal like a covert signal from some system and not provide the ability of an adversary to intercept that signal and do something with it. And of course, in cyber, it's very much the same way. Of course, today, on the offensive side, those involved in building offensive red team types of tools, we do take a lot of steps to try and protect our tools, binary diversification, code path obfuscation, you know, those sort of things that make things difficult for the adversaries to reverse engineer tools and capabilities. SGX doesn't obviate the need to do that. You still need to do that, and I'll show you why here in a little bit. But SGX gives you the capability to layer on more difficulty for your reverse engineer adversaries. And that's really what the game's all about. You're never going to make, we all know in this room, you're never going to make your software impervious to reverse engineering. You just, it's my opinion and the opinion of others, you just can't do it. So the idea is to make it so difficult, so expensive, and so hard that they either give up or, in some cases, just aren't able to do it, depending on their skill level. With SGX, Intel, I think, has handed us a really good tool to help out in this regard. Let's talk a little bit about the impact of all of this. Again, for the intelligence community, the major impact, the biggest impact is the CI, the counterintelligence problem that connotes, because if the adversaries can get into your tools, reverse engineering how you're doing things and how things work, that opens up a lot of bad things that could happen to you from the respect of counterintelligence. They can get in the middle of all that, and you wouldn't know about it. The human cost, they could track back, it's possible, depending on the systems, track back the human aspect, and you lose those capabilities. It's an opportunity for them, if they break into your systems, to provide misinformation and expose sensitive sources and methods. And that's one thing, sort of like jewels in the intelligence community, sources and methods. So when your tools get compromised, you lose sources and methods almost immediately. The OPSEC impact is very similar to the counterintelligence impact of losing tools, and that's you know, your OPSEC just absolutely goes out the window. And of course, the budgetary impacts are huge as well, because you have to replace those tools. You know, currently, in the wake of the Snowden exposures, in addition to that, there have been some other exposures, and so the intelligence community has to go and contract to have new tools and new capabilities built. And in recent years, we've seen a lot of RFPs and solicitations come out requesting what they call clean slate development, because, you know, they don't want the tools built on technologies that were previously compromised, and that's expensive. And so that drives up cost and your tax dollars. So the impact there in the intelligence community is real. In the private sector, a lot of parallels. The biggest impact in the private sector, of course, is loss of competitive edge. Because as I said, a lot of these companies, their key advantage in the market space is their intellectual property, something that they're doing that's interesting, unique, and sets them apart from their competitors. And when private sector loses their tools and capabilities to reverse engineering, they lose quite a big advantage. So Intel SGX, I think, has the opportunity to really help out in this regard. So we're going to talk a little bit about what SG is and how it works. Now, this talk is not so much about how it works. There's a lot of really good papers and discussions out there, although I'll cover a little bit of it here. I really want to talk to you more today about how you can start developing and working with SGX yourselves and putting together some compelling applications. In fact, you may even start a company or start marketing some of your products, because currently right now, because it's so new, it's pretty greenfield. It's pretty greenfield out there. And I'll talk a little bit about some of the ideas that we've seen kicked around lately. So with SGX, it's hardware-enforced protection of the memory, the application memory stack that's baked into the processor. It's implemented in microcode, and it's implemented by, I think it's 17 new instructions in the IA32 instruction set. And it's very similar to how they rolled out VTX. That also was implemented by roughly 17 instructions in the IA32 instruction set. And as you can see, they even look very similar to the VTX instructions, where you have enters, exits. They do have some debugging support, which is really important. Back in 2005, 2006 timeframe, I developed from scratch a hypervisor based on the VTX instruction sets, and I was working on the platforms before VTX was really released. And then when VTX finally came out and I could play around with it, there was no support for debug in that architecture early on. And so what I ended up having to do was program directly to the graphics card, and I was turning on individual pixels in the upper left-hand corner of my screen to tell me what went wrong. But with SGX, they've made things a lot more easy to deal with from a developer's perspective. So one thing that that Intel's done is they have taken a zero-trust approach to development. You can sort of look at, and it's been described in a lot of the literature and a lot of the talks that I've seen lately, as a reverse sandbox. So instead of trying to protect your code, try to protect the system from your code by sandboxing it, it's the reverse of that. What they're doing is they're assuming that the platform that your code is running on has been compromised, and that there's, compromised by the highest privileged code. They assume that there's a malicious hypervisor. They assume that the OS has been compromised. They assume SMM is compromised, and so they've set up these enclaves. There's something what they call enclaves on the application stack that protects the SGX code that you write and protects the code and data of your application as opposed to the other way around, which I think is an interesting approach. SGX implements all three of the major tenets of the trusted computing base, measurement, sealing, and attestation. And in fact, if you squint at SGX in just the right way, it really does look like a TPM, software-based TPM, because it has all the functionalities of that without having to rely on a TPM chip. So this is a pretty good model, I think, or diagram of what SGX does. And this image came from Intel's documentation, where you have your normal, stack there, where you have your code, the stack, and the operating system. But wedged in there is this thing called the enclave. It's the SGX enclave. And the way that's done is, when you fire up your SGX application, it reserves a segment of memory of RAM and seals that off. Then it will load your enclave code and data into the enclave, or the secure memory that it has set up, does a measurement on it, a hash, cryptographically signed hash, compares it, and if everything's fine, then it will launch the enclave and go. Once the enclave's up and running, nothing can see inside the enclave. Nothing. Not debuggers, not IDA Pro, not the system. You cannot see what's going on inside that enclave, and that's the real power and the real benefit of this approach that Intel's taken with SGX. Yeah. I'm not sure I quite understood that question, but the question is, correct me if I'm wrong, is when the OS is setting up the memory or this memory is requested, how is that controlled from a right? So, and how does the OS manage that? If you need to increase the memory, how's that handled and things like that? So, and that's a very good question, and I have a couple slides on that upcoming, but basically the way it happens is there are set sizes of memory that SGX will reserve for you. I think there's 3 different settings, and I have a screenshot about it. 128, 64, and maybe 32, I'm not sure. So it's like that. So it's not a lot of space, but when you think about code and data that you're trying to protect, you can do a lot in 128 bytes, right? And you can have multiple SGX enclaves running. But once it's set up, it's the OS, and this is where it gets a little bit tricky. And again, I'll refer you to some talks that happened at Black Hat recently and the recent IDF, where they get more into how it works. This talk is a little bit less of how it works, but how you can start programming in it. But it sets up the memory, it loads enclave code and data, measures it, and then it seals it. And then once it's sealed and initialized and ready to go, that's where it gets locked down. And you can't access that memory after that. Only SGX application can access that memory, and I'll show you. And you have to split it out. I hope that answered your question. So once the enclave is set up and sealed, the enclave it has its own entry table, has its own heap, stack, and has its own code. And again, the main point here is it now is an opaque black box on the application stack, which is a very, very good thing. And I'll show that here in a little bit. So once implemented in the proper way, as I said, you can't debug it with external debuggers. You can disassemble it, and I'll show you a little bit, but disassembly is really hard. And this is where I was saying earlier that you'll still want to implement code obfuscation, code path, dummy paths within your code to make it even more difficult. But SGX in and of itself makes reverse engineering very hard. There have been some claims, and I've seen some claims even in a recent Black Hat talk where they say it's absolutely impossible to reverse engineer an SGX enclave. And I don't find that to be true, although I haven't done a whole lot of work yet. I believe that you can get enough information that you can sort of see what's going on, but there's some things that Intel's doing in an upcoming version 2 release of SGX that are going to take care of some of those problems. And I'll talk a little bit about that as well. So I had given this talk, I was asked to come in and give this talk at CIA and up at NSA, a modified version of this talk. The talk I gave up there wasn't as technical. And so this slide was more for them because, believe it or not, there are a lot of folks in the intelligence community, not so much of NSA, but CIA. I hope there's nobody here from CIA, but they're not that well versed, not all of them, in assembly language programming. They can certainly look at assembly language dumps because they're working with IDA and all that stuff all the time, and in debuggers, but to actually, write assembly language codes, they kind of panic a little bit, as I think a lot of people do. So I know what maybe some of you are thinking, and certainly some in that community are thinking, is like, oh my God, we're going to have to develop assembly language code. We're going to have to, pour down through Intel's developer manuals. And any of you have done that, it's not unlike trying to read Beowulf at the conclusion of, say, DerbyCon last night. And they're very thick, they're very dense, and so it's really hard to discern. But fortunately, the opposite is true. So when Intel released SGX, they released a software development kit and platform software extensions as well. That really eases the process, and it only makes sense. Whereas VTX really was a kernel-level type of implementation, SGX is more an application, Ring 3 application stack implementation. So it really does make sense that they would create a very nice development kit, which they've done. So, and I should note for you Linux developers out there, as of late June, I think it was, Intel's made Linux versions of the SDK and the platform modules available. I've not personally played with it, but it is available, and I think that's a huge step on their part. So when you install the software development kit and the extensions for the OS, lo and behold, when you fire up Visual Studio, there at the very top of the list of templates you have available to you is SGX enclaves. And so it doesn't get much easier than that. And then when you create those projects, just like you would any other project, it'll pre-populate some of the header files for you and give you a really good head start on just like writing your code. So on the development side, normally we have, the standard development model where you declare your functions either in the file or as extern. Then you write your main, and you call those functions, right? So, of course, when those applications are running on platform, they're sort of wide open to disassembly, reverse engineering. You can get a really good sense, even if they're obfuscated, on what's happening and how it's happening, and discern all that. When you're developing or designing an SGX application, the idea is that you want to spend a little bit of time thinking about what in my application do I really want to protect? What code and what data do I want to protect? And you decide, we're going to put that in the enclave. Now, as I mentioned earlier, I think the largest enclave size that you can reserve is 128. And again, although you can put a lot in there, you're not going to want to run your entire application in an enclave. Although I've seen guys do that, it gets a little unwieldy. And so the recommendation is that you do some thought up front and decide, what is it in this application do I really want to protect? Could be an encryption algorithm, could be how certificates are handled, could be if you're developing, say, a CoveCom system where you would want to protect, again, in that case it would be the encryption algorithm. And I'll talk about it in a little bit. There have been some interesting projects where they've written plugins to Chrome and other browsers as SGX applications, and then they handle all the cert functions in the enclave. And the rest of your code can be out, just out there normal. So now it's demo time, and see, this is a really exciting part for you guys because this is an opportunity for me to really sort of flame and crash, and so I guess in some senses that can be entertaining. So. Why don't we go ahead and get into this? Whoops. So the first demo I wanted to show you is a little bit about the application. Is that Do I need to zoom in on some of this stuff? Yeah. Can we do anything about the lights in here? Is there one up here, Matt? There we go. Is that better? Oh. Yeah, no, I can't see my slides now. Oh, muddle turned it. I don't care about the camera seeing me. Yeah, that's better. Thank you. Can you still see? Can you see the screen a little bit better? So, get my notes here and see what I. The first thing I wanted to show you was. I need to back up here a second and show you that I won't show you. This is a little bit too difficult. My mouse is sliding downhill. So it's at the SGX application is actually broken up into two different parts. You have the application, the straight up application that's going to call your SGX enclave, and then you have your SGX enclave. And what I pulled up here is the actual enclave code. And so the enclave essentially compiles to a DLL. You have different, within the SGX template, you have several different compile methods. You have your standard debug. There's a pre-release version, release, and a simulation. Now the simulation is interesting, and I haven't played with it, but simulation will allow you to write and play around with SGX applications if you don't have a platform that supports SGX. It will emulate it for you, and you can make sure that your code is working okay, but make no mistake, they're not going to be secure. You're still going to be susceptible to memory forensics and reverse engineering, but at least it gives you something you can play around with until you can get a machine that supports SGX natively. Again, when you open up the project, it pre-populates a lot of these pre-compiled headers for you and places them in there. And then what you need to worry about is actually writing your code. Now, in this little quick, dirty test application that I put together, it's basically an extreme secret crypto function, but basically all it does is it reverses the string. And my secret data here is the string mange merde, and that's important. And remember that, because when I get into the demo where we're doing memory forensics, we'll want to look for that. We'll want to look for that string. So in and of itself, it should be very familiar. Again, you're just writing essentially a DLL. It does produce what's called an EDL file, and that's an enclave descriptor language, and it builds that for you. It actually doesn't build it for you. What it does, it creates this empty structure. And so what you need to do is, in this structure, this enclave structure, you want to define your enclave functions that you want to allow. So the trusted e-calls are your protected functions. They're really prototyped here. And so in this particular demo, we only have one function that we're dealing with, and that's our extreme secrets crypto function, and it has to go into the EDL file. They also have a place here for untrusted O-calls or out calls, and those would be calls that you would make or would need to make from within your enclave back out into the untrusted world. But honestly, I can't think of any reason why you would want to do that. I'm sure there must be a reason. Intel wouldn't have put it in there if they didn't think there was a reason. But I can't think of any reason why you would want to make untrusted calls from within the enclave to the outside world. So let me get out of that. So now let's look at the standard application that we're going to use to call our enclave. And this is the second part of that. And it's just, in this case, just a test application. Now, and again, this is just a standard application. This is not really your enclave, but this is the application that's going to call your enclave. The template sets up, again, some of these pre-configured headers. These pre-configured headers here. You do have to populate this, and there's some guides online to do that. And here is within our function or in our applications where we call that enclave function right here. There's a string secret. And then after that's done, it will destroy your file. Now, what you do have to do in your application is you have to, and again, this SGX configuration is all part of the template structure, you have to import the enclave. And so you go over here, you find the enclave that you want to import, double click it, and then check it and import it, and that's it. So then you just compile it normally like you normally would, and then you can test your application. So let's try that. Oops. And so we get these messages that I programmed in there that the SGX enclave's created successfully. The buffer before I called the SGX enclave was just greets from outside the enclave. That was included in the application, test application. Then it calls into the enclave and it takes my secret string mange merde and reverses it and then done. And so then it destroys it. Now the purpose of that really wasn't to show you how I can write, really cool crypto stuff. It was more just sort of, that's the flow. And as you can see, the major point here is that it's standard development. You don't have to invest in a lot of research and development. It's already stuff that you're doing now if you're developing Visual Studio kinds of applications. So the learning curve to get to SGX and start playing with it is extremely low, and it makes it very attractive. And in fact, if some of you are working with interns, I know we're probably past the intern season now, but it's really conceivable that that would be a nice intern project to assign and have them start developing some interesting SGX applications for you. And there actually is some interest in the government in SGX, and I'll tell wasn't really a humorous story, but it was kind of funny in a way. I had become aware of SGX through some contacts up at Intel back as early as 2012, and thought, this is some pretty interesting technology, and I think, the government should probably show some interest in this. And so I began briefing them about it and got them, a little bit excited about it. But government being the government, they never really showed much interest in terms of setting up a budget, setting up a program, and going after it, and essentially just sort of let it drop. And it was kind of funny, a colleague of mine just about 6 or 7 months ago was in a meeting with the customer, and the customer after the meeting pulled him aside and said, "Hey, have you guys been following what's going on with this Intel SGX stuff?" We're like, "Yeah, for the last 2 or 3 years we've been trying to get your attention on it." So anyway, there is some interest inside the government now in SGX, and so if you work for companies that support that community, it may be a good idea to start maybe prototyping stuff, talking to your COTRs, and getting in front of them with some interesting stuff. And even if you're not a current contractor, because the entry into developing this technology is so low, you can actually probably go in unsolicited and show them some things, and it's a good chance that there may be some interest in it. So anyway, just sort of my tip to you on that. Let's see if I've covered everything I wanted on that demo. Yeah, so So naturally, once I've started, being able to get some SGX stuff compiled and running, because the reason that Intel SGX really exists is to protect memory, volatile memory, from your code, your sensitive code, and your sensitive data. One other feature, and I forgot to mention earlier, is that nothing leaves the processor that's in your enclave, your protected stuff, unencrypted. It never leaves the processor unencrypted, and that's huge. And so I really wanted to test that theory out, and so naturally I gravitated to volatility. I took Matt's course earlier this week on in-memory coding, and I was mentioning to him I had some difficulty finding some of the legacy tools, and so I ran across this Magnet. It's a free utility out there that will do Windows dumps for you nicely. So I used Magnet and volatility, and so what I wanted to do is look in the memory dumps for my secret data in that code, specifically looking for Mange-Merde and looking for my extreme secret function call. So lo and behold, even though I had compiled my code at pre-release, and the Intel documentation says the pre-release profile in terms of debug symbols is the same as release. I know I found that was true, but it doesn't, the pre-release version, pre-release builds does not protect yet from, strings being copied into memory and being acted on. So I did a little bit of digging on that, and it turns out Intel has this really, I'll call it weird, licensing tier structure for SGX, naturally because it's a new technology that's very protective. And so able to compile release versions of your SGX enclave code, you have to have what's termed by them a production license. And so I went down that road, and from my work with Intel, with my own company, I had an NDA in place with them already. Step one in getting your production license from Intel with this is you have to have an active NDA. Then you have to exchange, certification files, and then you have to engage in a series of interviews with Intel engineers and Intel business development folks, and they have all kinds of questions for you about, well, what exactly are you trying to build? What's the product that you're trying to, product market that you're going after? Do you have in place, you know, all the controls for protecting certifications and all those sort of things? Well, unfortunately, I didn't have my social engineering hat on when I went through that interview process, and basically told them, hey, look, I'm giving a presentation at an upcoming HackerCon. That was probably a mistake, and I wanted to demonstrate the effectiveness of SGX in protecting sensitive code and data. Well, they immediately turned down my request, and they said basically, we don't give out production licenses for demo purposes. Fair enough. So I wasn't able to get a license protection, but they do have this intermediate licensing agreement that gives you access to their remote attestation server. SGX supports this model called remote attestation, where you can go out and say to an external server, is this SGX enclave valid? And we'll assist in the sealing and the attestation process of your development. And so, and that again requires an interview, and it's a long process. Well, 2 days before flying down here, I finally got what's called my SPI. Unfortunately, I haven't had a chance yet to do that, but all's not lost. Interesting thing is, when you install the Intel SGX platform software kit or modules, Intel loads onto your system a couple of Intel enclaves themselves. Now let's stop and think about that a minute. Intel is loading and installing enclaves, valid enclaves, onto your system to help with the process. And then going back to what I've said is, it's very difficult to reverse engineer enclaves. They're essentially black boxes. So you can't tell, at least I can't tell yet, what exactly is that enclave doing, right? You don't know. And so you sort of see the problem or the advantage of using SGX to protect your tools, because it really is difficult to find out what's actually going on. So if you were a malicious guy, say you're developing malicious codes, or even pen testing codes for that matter, you might want to include in your enclave code some cover application, say, you know, a Pokemon management system or whatever. But along with that, you have your encryption routines for exfiltrating data that you're collecting on the platform. And so, again, going back to this idea, and being paranoid as most of us are, I don't like the idea that Intel is loaded and is running enclaves, like full blown up enclaves, on my machine. So in the next demo, I'm going to show you what that looks like from a forensic perspective. But as you can see from this slide, when I looked at my volatility dumps, I found my my secret data string, mange-merde, right in there. And there were 3 references to it. Now, certainly it was in free memory, but it was in there, and didn't like that at all. I did find some of the code that I didn't want to see in there running, but this code actually is from the application, the non-enclave application part. So let me do that real quick. I'm running behind time here. Yeah, let me show you this first. I'm going to show you what it looks like trying to debug an enclave outside of the development environment. They do provide, Intel's development kit does provide debugging facilities, and that's the only place you can debug enclaves. So let's set a breakpoint. So I refer to my notes and make sure I don't type it in. incorrectly. So what I'm going to do is set a breakpoint on the my extreme secret crypto function. It'll give you this weird message where it can't find the symbols, but that's okay. And so here we hit our breakpoint. So if I disassemble it, I can start to see some of the disassembly here. But again, this is the application, not the enclave code. What I really wanted to show you in the enclave code, or the application itself, you can see that the enclave failed to launch. And so, in a way, it's protecting itself that way because it won't allow you to launch an enclave outside of the debug facilities, and if it's not valid, if it can't validate that the SGX enclave is real and measured and attested to, it just will fail to launch. If you have an honest-to-God one and it's all set up and going, what happens then is the enclave itself becomes one, with respect to the debugger, one executed piece of line of code. So you can't step through it and you can't see what it was doing. Oops, still running it in debugger. So in IDA, one that I want to show you is this PSE opsign DLL. This is the Intel's DLL enclave that is valid. So as you can see, can you see that screen very well? Should I blow that up a little bit? So as you can see, strings or symbols are definitely not there. You can see all these sub things here. If you look at strings, they're all really just kind of gibberish. There's only two strings in there that make any sense, and those are the exported function calls. These two, the enclave entry and this something called GP keep used, which just by its own name is an interesting name. So let's take a look at the entree code. As you can see, it's actually fairly reasonable. I think you could probably disassemble this or like understand this pretty well. So, you know, the claims that others are making that you can't, it's just not reverse engineering, just based on what I'm seeing here, I think it's possible to reverse engineer it. It may be difficult, but I don't think it's impossible. And of course, there are absolutely no imports. Now let's take a look at this other one here, this G heap. Now this looks a little more difficult than the entry point. So you can see there's a lot of undeclared parameters there, or uninitialized parameters. It really, it's kind of a mess in terms of reverse engineering it. You can use some of these jumps or XREFs to go through and try and paste together what it's doing, but it makes it very difficult. And again, going back, if you continue to put obfuscation in there, some fake code paths, it will make it even very difficult for your adversaries. I'm going to finish up here real quickly. We've got to get on to the next speaker. So, SGX availability. There are a tremendous amount of processors available today that support SGX. And this is the list. And this list is current as of two months ago. So Intel does this really weird thing about their SKUs and how they name their products. For some reason, the SGX chips, they all have the same SKU number on them, but there's this thing called post-conversion S-spec, and that's what you want to look for. You want to look for the R in the, hold on a second to make sure I'm telling you the right thing. It's either the R or the L. The L. You want to look for the L code in the this L1, L2, L3. You want to look for that. If SGX is not supported, there's an R there. When I went to Micro Center the other day to look at them, every one of them of this new Skylake processor was of the L variety. So all of them supported SGX. There are some systems out there that you can buy today that are already set up, ready to go. BIOS supports it. This Inspiron laptop I have is one of them. Cost me less than $500. So there are available, and you can start playing around with it. So when you look at the BIOS, you can, and sorry about the slide, but it's a very exciting moment when you look in the BIOS and find out that, oh wow, SGX is absolutely supported here. The key point here is that SGX is not implemented in BIOS by default. And that's a problem if you're running offensive operations, because, you know, if your target's not using SGX, it's difficult if they haven't implemented it. But I'll refer you back to VTX. When Intel rolled out VTX, they didn't have it set as default, but now it is. So hopefully in the future, it'll be set by default, and then it's like Katie, bar the door. Here's what I was talking about where you can set the SGX memory size. 32, 64, and 128. And again, you can do a lot of malicious things or interesting things in 128 megabytes. So some interesting SGX projects that are going on right now. Bromium at last month's IDF presented a talk on their extensions to the Google browser, and they're securing their users' certificates using a browser plugin. Microsoft is going after SGX in a big way, but their focus is on securing cloud instances. Personally, I think that's where the action is going to be. My next step in research is actually going to be looking at securing cloud instances. And again, going back to this concept of a reverse sandbox, you don't know what's going on out there in the cloud. You don't know what your cloud service providers are doing in terms of the data, the insider threat there, and SGX can go a long way in alleviating concerns. We find that one of the biggest concerns in companies moving stuff to the cloud is that insider threat at the cloud service provider. SGX eliminates that threat completely. And just think about the market there for like hedge funds managers, insurance companies, and all that. So cloud, I think, is where it's going to be. Again, to get started with SGX, very simple. They've sort of really made it easy for you to do it. You just need a Skylake processor and, of course, a motherboard that supports it and a BIOS that supports it. You need the SGX development kit from Intel, which is free. Their platform extensions. and then you're off to the races. A little bit about the future, where I see the future going. SGX version 2 is coming out probably a little bit later this year, and it does fix a couple things that currently aren't supported in SGX. Dynamic memory allocation and protection sort of goes to your question a little bit, I think. Exception handling. Right now, SGX doesn't report exception handling. General protection falls back to the enclave. They need to do that. That's being fixed. This next one I was less concerned about, the RDT, the timestamp stuff. I don't get why that's a big issue. And thread level storage, they're fixing that. There really isn't any reason why anybody in this room shouldn't or couldn't start playing around and developing SGX applications, and I really do encourage you to do that. Again, tools compromises, intellectual property theft is a big deal, and I think it's incumbent on us to do everything we can to thwart that, and I think SGX is a really low threshold barrier in doing that, and would encourage all of you to consider doing it, getting out there and doing it. I would say I'd take some questions, but I'm already over time. If we can do it offline, the next speaker, he needs to get on, so I'll hang out here and you can answer your questions. So again, thank you so much for coming to such an early Sunday morning presentation, and I hope you found some value in this.